Physics did not change overnight. It hesitated. It argued with itself. It stood at the edge of certainty and doubt. At the dawn of the 20th century, classical physics explained the visible world with confidence, but the atomic world refused to obey its rules. Something new was needed, yet something old could not be abandoned. What I attempted was not to destroy classical physics, nor to worship quantum theory blindly, but to build a bridge between them. A bridge where contradiction could coexist with understanding. At the beginning of the 20th century, classical physics stood as a monument of certainty. It explained motion through Newton, energy through thermodynamics, and light through Maxwell's electromagnetic waves. To many, it seemed that the book of physics was nearly complete, with only small details left to refine. Yet this confidence rested entirely on phenomena visible to the human scale. When attention turned toward the atom, the very foundation of classical thought began to fracture. The atom was first approached with classical intuition, imagined as a tiny mechanical system governed by the same laws that ruled planets and pendulums. Electrons were treated as charged particles moving in well-defined paths around a central nucleus. According to classical electrodynamics, however, such motion carried an unavoidable consequence. A charged particle in acceleration must radiate energy continuously. An electron circling a nucleus is constantly accelerating, and therefore it should emit radiation, lose energy, and spiral inward until it collapses into the nucleus. This prediction was precise, logical, and entirely wrong. The stability of matter presented a profound paradox. Atoms did not collapse. They maintained fixed sizes, emitted light at specific frequencies, and exhibited remarkable regularity. Classical physics could not account for why atoms were stable, nor why they emitted discrete spectral lines, rather than a continuous range of colors. Spectroscopy revealed that each element produced a unique pattern of sharp lines, as if atoms were tuned to specific frequencies. Classical theory predicted no such selectivity. It allowed all energies and all motions, yet nature permitted only a few. This was not a minor inconsistency, but a fundamental crisis. The failure extended beyond atomic stability to black body radiation, where classical theory predicted infinite energy at short wavelengths, an outcome that was physically absurd. Attempts to patch these problems within the classical framework only deepened the contradictions. The equations themselves were internally consistent, yet they no longer corresponded to reality at small scales. The deeper issue was continuity, a principle woven into classical physics at every level. Energy was assumed to vary smoothly, positions to be precisely defined, and trajectories to exist independent of observation. At the atomic scale, experiments began to suggest that nature did not respect these assumptions. Energy exchanges appeared to occur in sudden jumps. Certain states were allowed, others forbidden, without any classical explanation for why such restrictions existed. This realization was deeply unsettling. Classical physics was not merely a collection of formulas, but a way of thinking about the world. It assumed that with enough precision, one could predict the future state of any system. The atomic world resisted this worldview. The more carefully it was examined, the more it revealed behaviors that could not be reconciled with classical determinism. Some physicists initially believed that these difficulties reflected incomplete measurements or experimental errors. But as evidence accumulated, it became clear that the problem was theoretical, not technical. Classical concepts such as orbit, velocity, and radiation could not all be applied simultaneously without contradiction. The language that had served physics so well was becoming inadequate. What troubled me most was not that classical physics failed, but that it failed precisely where it should have been most reliable. The atom was not chaotic or unpredictable. It followed strict rules, but rules of a different kind. The challenge was to recognize that the limitations lay not in nature, but in the concepts we imposed upon it. This crisis forced a choice. Either physics would abandon its successful classical foundations entirely, or it would find a way to extend them without denying their validity. I did not believe that centuries of understanding had suddenly become meaningless. Classical physics worked perfectly in its proper domain. The difficulty arose when its principles were extended beyond that domain without question. The atomic scale demanded new principles, but those principles could not exist in isolation. They had to connect back to classical results where classical physics had proven itself. The breakdown of classical theory was therefore not a destruction, but an invitation to reconsider the scope of its applicability. In confronting the crisis of classical physics, we were compelled to accept that our descriptions of nature are shaped by the conditions under which we observe it. The atom could not be visualized as a tiny machine without distortion. It required a new framework, one that acknowledged both the success of classical physics and its boundaries. One that accepted that certainty itself might have limits imposed by nature rather than by human ignorance. When I introduced quantization into the description of the atom, I did not do so because it felt natural or intuitive. On the contrary, it was a deliberate departure from the mechanical images that had guided physics for centuries. Classical physics demanded continuity. Motion was smooth, energy flowed without interruption, and change occurred through gradual transitions. Yet the experimental evidence from atomic spectra left no room for such assumptions. Nature itself was signaling that continuity could no longer be taken as an absolute principle at the smallest scales. The discrete nature of atomic spectra was impossible to ignore. Each element emitted light at precise frequencies, forming sharp lines rather than a continuous band. These lines were not accidental. They followed strict mathematical regularities. If atoms behaved as classical systems, their radiation would vary smoothly with energy and time. Instead, atoms appeared to recognize only certain values, rejecting all others without compromise. The challenge was not merely to explain these observations, but to do so without inventing imaginary mechanisms that contradicted known facts. Quantization, as I proposed it, was not a picture of electrons leaping through space like mechanical objects changing gears. It was a rule imposed on the structure of the atom. Certain states were allowed, others were forbidden, and transitions between them occurred without any description of what happened in between. This was deeply unsatisfying to classical intuition, which demanded a continuous story. But the demand for a story had to yield to the demand for consistency with experiment. In the atomic model I developed, electrons were permitted to occupy only specific stationary states, while in these states they did not radiate energy, even though classical electrodynamics insisted that they must. Radiation occurred only when an electron transitioned from one allowed state to another, emitting or absorbing a quantum of energy equal to the difference between those states. This rule did not describe a process in time as classical physics would. It simply stated the conditions under which observable phenomena occurred. This approach was radical because it replaced mechanism with constraint. Instead of asking how an electron moved at every instant, the theory specified which configurations were possible and which were not. The emphasis shifted from trajectories to conditions. Quantization became a structural principle rather than a dynamical one. It defined the architecture of atomic behavior without appealing to familiar mechanical causes. Many found this deeply troubling. Physics had long been built upon visualizable models. One could imagine gears turning, particles colliding, or waves propagating through space. Quantization resisted such imagery. The stationary states of the atom could not be drawn as classical orbits without contradiction, yet they produced correct predictions. The success of the theory forced us to confront an uncomfortable truth. Understanding in physics does not always require visualization. What mattered was not whether the model resembled everyday experience, but whether it faithfully reproduced observable results. Quantization allowed us to calculate spectral lines, atomic sizes, and ionization energies with remarkable accuracy. It restored stability to the atom without resorting to arbitrary assumptions. The price paid was the abandonment of classical continuity at a fundamental level. This shift had profound philosophical consequences. It suggested that nature does not permit all conceivable motions, but only those that satisfy certain quantized conditions. These conditions were not derived from classical forces, but imposed as fundamental rules. The atom, in this sense, behaved less like a machine and more like a system governed by principles of selection. Yet quantization was never intended to overthrow classical physics entirely. It was introduced precisely where classical reasoning failed and nowhere else. In regions where energies were large and scales were macroscopic, the effects of quantization became negligible and classical behavior re-emerged naturally. This coexistence was not accidental but essential. Any new theory had to respect the successes of the old one. Quantization thus served as a bridge rather than a barrier. It acknowledged the limits of classical explanation while preserving its validity within its proper domain. The atomic world required rules that could not be reduced to classical mechanics, yet those rules had to converge toward classical results when applied to familiar systems. This delicate balance defined the early development of quantum theory and shaped the way we would come to think about physical reality at its most fundamental level. As quantum theory began to take form, it became clear that the greatest danger was not error, but disconnection. New ideas were emerging rapidly, driven by experimental necessity rather than philosophical comfort. Yet without a guiding principle, these ideas risked becoming isolated fragments, unable to relate to the well-tested structure of classical physics. It was in response to this danger that I formulated what came to be known as the correspondence principle, not as a rigid law, but as a methodological guide for understanding the transition between quantum and classical descriptions. The central insight behind this principle was simple, though its implications were far-reaching. Any theory that claimed to describe nature more completely could not contradict the established successes of classical physics in the domain where classical physics had already proven itself. Planetary motion, electromagnetic waves, and thermodynamic behavior did not suddenly become false because atoms obeyed different rules. Instead, quantum theory had to reduce to classical results when systems became large, energies increased, or quantum numbers grew sufficiently high. This requirement provided an anchor during a period of conceptual uncertainty. Quantum rules were often introduced in ways that defied intuition, relying on discrete states and abrupt transitions. Without a connection to classical results, these rules could have appeared arbitrary. The correspondence principle ensured that the strange behavior of atoms was not an isolated mystery, but part of a continuous hierarchy of physical description. In practical terms, the principle guided calculations at a time when the mathematical formulation of quantum mechanics was still incomplete. By demanding agreement with classical predictions in appropriate limits, one could test whether a proposed quantum rule was viable. If it failed to reproduce known classical behavior under those conditions, it could not be correct. In this way, classical physics became a standard against which quantum ideas were measured, rather than a theory to be discarded. The principle also clarified the meaning of quantization itself. Discrete energy levels were not in conflict with classical motion when considered properly. At high energies, the spacing between quantum levels became so small that they effectively merged into a continuum. Under these conditions, the smooth behavior predicted by classical physics reappeared. What seemed like a radical break at small scales became a natural extension when viewed across scales. This gradual emergence of classical behavior from quantum rules revealed that the two descriptions were not rivals but complements. Classical physics described the average behavior of systems where quantum effects were blurred by size and complexity. Quantum theory described the fine structure underlying those averages. The correspondence principle articulated this relationship without requiring a single unified picture that would satisfy all intuitions at once. Equally important was the role the principle played in shaping our expectations of explanation. It cautioned against demanding classical visualization in regimes where it no longer applied. Instead of forcing quantum phenomena into familiar images, the principle encouraged physicists to focus on the consistency of predictions across domains. Agreement with classical results became a criterion of adequacy, not a demand for classical imagery. The correspondence principle also carried a deeper epistemological message. It suggested that our descriptions of nature are layered, each appropriate to a certain range of experience. No single level of description holds absolute priority. Classical concepts retain their meaning and usefulness precisely because they arise as limiting cases of more general principles. Quantum theory did not invalidate classical physics, it contextualized it. This perspective was essential in preventing the fragmentation of physics into incompatible frameworks. Without the correspondence principle, quantum theory might have evolved as an entirely separate language, disconnected from the physical intuition developed over centuries. By insisting on continuity of results, if not of concepts, the principle maintained coherence within the discipline. The success of this approach reinforced the idea that physical theories are not mirrors of reality in a naive sense, but tools for organizing experience. Their validity depends on the conditions under which they are applied. The correspondence principle made explicit that no theory can be judged in isolation from the domain of phenomena it seeks to describe. Through this principle, the transition from classical to quantum physics became intelligible, not as a sudden rupture, but as a gradual shift in applicability. It allowed physicists to navigate a landscape where old certainties no longer held universally, without abandoning them entirely. In doing so, it provided a bridge sturdy enough to carry understanding across the boundary between the familiar and the fundamentally new. As quantum investigations progressed, it became increasingly evident that the difficulty was not merely mathematical, but linguistic and conceptual. The classical language inherited from everyday experience and refined through centuries of physics was being stretched beyond its limits. Concepts such as position, momentum, wave, and particle had acquired precise meanings within classical contexts. Yet, when applied to atomic phenomena, they produced contradictions that could not be resolved by further refinement. This tension demanded not a correction of equations, but a re-examination of how physical descriptions are formed. The behavior of light and matter offered the clearest illustration of this problem. In some experiments, light behaved unmistakably as a wave, producing interference and diffraction patterns that could not be explained by particle models. In others, it appeared as a stream of localized energy quanta interacting with matter in discrete events. Attempts to combine these pictures into a single classical image failed because each description excluded the conditions required for the other. The experimental arrangement determined which aspect could be observed, and no arrangement allowed both to be displayed simultaneously. From this realization emerged the principle of complementarity. It did not claim that nature was contradictory, but that our classical concepts were mutually exclusive when applied beyond their proper domain. Wave and particle descriptions were not competing explanations of the same phenomenon, but complementary accounts, each necessary for a complete understanding, yet each applicable only under specific conditions. The limitation lay in our language, not in the phenomena themselves. This principle extended beyond light to the behavior of electrons and other quantum entities. An electron could be described as having a definite position when measured with an apparatus designed for localization. Under such conditions, its momentum became indeterminate. Conversely, experiments that revealed well-defined momentum distributions required arrangements that obscured precise position. These were not technical imperfections, but fundamental constraints. The experimental setup did not merely reveal properties, it defined the conditions under which those properties could be meaningfully discussed. This principle did not diminish the explanatory power of physics. On the contrary, it expanded it by acknowledging the limits of what could be said without contradiction. It allowed physicists to use classical concepts effectively while recognizing that their applicability was conditional. The completeness of a description was no longer judged by its ability to present a single unified image, but by its capacity to account for all observable phenomena through a coherent set of complementary perspectives. Complementarity thus represented a profound shift in scientific thinking. It replaced the demand for absolute descriptions with an acceptance of contextual ones. In doing so, it preserved the precision and communicability of physics while freeing it from the constraints of an outdated conceptual framework. The atomic world did not conform to our inherited categories, and complementarity provided a way to speak about that world without forcing it into forms it could not sustain. Measurement, therefore, does not simply uncover pre-existing values. It establishes the context in which certain properties can be defined and communicated. The outcome of an experiment depends not only on the system, but on the entire experimental arrangement. The measuring device, described in classical terms, becomes an essential part of the phenomenon, even though it lies outside the quantum system itself. This realization required a careful distinction between the quantum system and the classical framework used to describe experiments. While the atomic object follows quantum laws, the measuring apparatus must be described using classical concepts in order to ensure unambiguous communication of results. Without this classical description, experimental outcomes would lose their meaning. Paradoxically, quantum theory depends on classical language for its formulation, even as it reveals the limitations of that language. The observer, in this context, is not an individual consciousness imposing subjectivity, but a necessary reference point for defining experimental conditions. Physics remains objective in the sense that results are reproducible and communicable. However, objectivity no longer means independence from observation. It means clarity about the conditions under which observations are made and statements are valid. This shift altered the notion of causality that had dominated classical physics. In the classical view, complete knowledge of initial conditions guaranteed precise prediction of future behavior. Quantum mechanics replaced this certainty with probabilistic predictions, not due to ignorance, but due to the structure of the theory itself. Measurement outcomes could be predicted only statistically, even when experimental conditions were fully specified. The statistical character of quantum predictions does not imply randomness in a trivial sense. It reflects the limits placed on simultaneous knowledge of complementary quantities. The act of measuring one property necessarily restricts the precision with which another can be defined. These limitations are not imposed by human inadequacy, but by the fundamental conditions required for measurement. The role of measurement also clarified why questions about what happens between observations often lead to confusion. Classical reasoning encourages us to imagine continuous processes occurring independently of observation. Quantum theory warns against such extrapolations. Statements about unobserved properties lack meaning unless they can be connected to a specific experimental arrangement. The theory does not deny the existence of reality between measurements, but it restricts what can be said about it. This perspective preserved consistency at the cost of abandoning certain classical intuitions. It required accepting that physical descriptions are tied to the conditions under which evidence is obtained. Measurement is not an intrusion into an otherwise well-defined reality, but a bridge between the abstract formalism of quantum theory and the concrete world of experience. By recognizing the active role of measurement, physics avoided the paradoxes that arise when classical assumptions are applied indiscriminately. The observer became part of the description, not as a source of arbitrariness, but as a necessary element in defining phenomena. This understanding reinforced the idea that the aim of physics is not to reveal an independent reality stripped of all conditions, but to establish reliable relations between experiences that can be clearly communicated and consistently reproduced.